Hello friends, welcome to this video about how to perform the addition and subtraction of signed binary numbers using the 2's complement form. As you know, signed binary numbers are those provided with a sign and so include positive as well as negative binary numbers. The objective of this video is how to take advantage of the 2's complement form to make the addition and subtraction of signed binary numbers. The use of the 2's complement form is particularly useful when managing negative numbers. In the following explanations, it is assumed that you have practiced the content of our previous video, 1's complement and 2's complement, where the conversion methods are explained. It is a short video, so I recommend you to check it first. Let's first highlight some important concepts. Computers do not know about the negative sign, only know 0 and 1. To represent negative numbers, computers use a system called 2's complement conversion, by which instead of doing a subtraction, they do an addition. The 2's complement conversion consists in two consecutive changes. First, invert the number, and second, add 1. The idea of the 2's complement is very powerful because to perform a subtraction, we can use the same logic circuit for an addition. For example, in this equation, the negative number minus b can be represented by the 2's complement. And in this way, the subtraction has been converted into an addition. Computers are defined by the number of bits they can manage. So we say 16-bit computer, 32-bit computer. How these bits are distributed is very significant. So, when doing arithmetic operations with signed numbers, the most significant bit is dedicated and reserved to the signed representation. It is called the sign bit. It is 0 if the number is positive and 1 if it is negative. Now I will talk about the 2's complement arithmetic properties. The first is that any negative binary number can be represented by its 2's complement. So, minus n and the 2's complement of n is the same. And the second is that if we apply 2 times the 2's complement to a number, we come back to the same number. That means 2's complement of n is equal to minus n. And 2's complement of n is equal to n. Example, the number plus 6 in binary is 0, 0, 1, 1, 0. If we make the conversion, first we invert the number, and then we add 1, and we get the number minus 6. And now, if we make the conversion again, you can see that we come back to the same number. So, applying 2 times the 2's complement to a number, it returns to the same number. With these two properties in mind, let's analyze the different cases that can occur when adding or subtracting two signed numbers a and b. This in case of addition, and this in case of subtraction. As you can see, by substituting the negative number by its 2's complement, all cases have been converted into additions, even when a and b are negative numbers. Minus a minus minus b is equal to 2's complement of a minus 2's complement of b. And minus 2's complement of b is 2's complement of 2's complement of b, so it is plus b. So, in this manner, using the 2's complement, all additions and subtractions can be converted into additions. Addition, 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 and addition. So, to perform a subtraction, we can use the same logic circuit for an addition. Now, before going further with some practical examples, I want to draw your attention to the following precautions when adding or subtracting binary numbers. The first is range. While performing the additions or subtractions, we should always be careful about the range and its range limits. With n bits, we can represent signed numbers from plus 2 to the n minus 1 minus 1 to minus 2 to the n minus 1. Example, with 5 bits, we can represent integer numbers from plus 15 to minus 16. If the result is out of range limits, we will get an overflow, and we will get an invalid result. Example, 9 plus 7 is 16. Using 5 bits, we will get the message invalid result, because maximum number which can be represented is plus 15. And another example with negative numbers, minus 8 minus 9 is equal to minus 17. Using 5 bits, we will also get the message invalid result, because the maximum number which can be represented is minus 16. Increasing the number of bits. This means if we get an invalid result using a certain number of bits, we can try with an increased number of bits, because by using higher number of bits, the result may not overflow. Now, a little trick to quickly realize if an addition is incorrect. The trick is looking at the sign bits. For example, if both a and b are 0 and the sign bit of the sum is 1, then the result is incorrect, because we are adding two positive numbers. Therefore, the result has to be positive, and so the sign bit of the result should be also 0. This error happens often when there is an overflow. Following, we will see a few practical examples of addition and subtraction using the 2's complement method. First, we will see some examples that provide valid results, results that are correct. In blue are the decimal numbers, and in black the corresponding signed binary numbers. As you can see, all the examples are using 5 bits. The first is the addition of two positive numbers that, converted into decimal, correspond to the addition of plus 7 plus 8 equal plus 15. As you see, the most significant bit of each binary number is 0, which means that they are positive. The result of the addition is correct, and it is verified by the calculation conversion. The second example is the addition of a negative number and a positive number. This is shown by the most significant bit of each addend, 1 and 0. Converted into decimal, it represents the addition of minus 15 plus 9 equal to minus 6. So, the minus 15 has been converted into the 2's complement in order that we can operate the sum like a normal addition. The result of the addition is correct. and has been verified by the calculation conversion. The third example is the addition of two negative numbers, as it is shown by the most significant bit of each addend, which is 1. 1, 1. Converted to decimal, it represents the addition of -8 plus -5 equal to -13. So, the two numbers have been converted into the 2's complement. So we can operate the sum like a normal addition. The result of the addition is correct and has been verified by the calculation conversion. Note that the sum of the last column produces a carry out of the 5 bits, so it is ignored. This is the normal practice because do not participate in the addition. So, the 5 bits result is correct, as verified by the calculation conversion. Now we will see a couple of practical examples of addition and subtraction generating an invalid result. The first example is the addition of two positive numbers that converted into decimal correspond to the addition of +11 plus 7 equal to +18. As you see, the most significant bit of each addend is 0, 0, 0, meaning that they are positive. Looking at the most significant bit of the result, we can quickly realize that the addition is incorrect because we are adding two positive numbers. Therefore, the result has to be positive. So the sign bit of the sum should be 0, which is not. The reason for the invalid result is due to overflow out of the range limits, because with 5 bits we can only represent numbers from +15 to -16, and the result is +18, so out of the range. As you can see here, there is the same operation increasing the number of bits from 5 to 6. 1, 2, 3, 4, 5, 6. The result using 6 bits is correct and has been verified by the calculation conversion. The second example is the addition of two negative numbers as it is shown by the most significant bit of each addend, which is 1. 1, 1. Converted into decimal correspond to the addition of -8 plus -9 equal to -17. The two numbers have been converted into the 2's complement form. 2's complement form. So we can operate the sum like a normal addition. Again, looking at the most significant bit, we can quickly realize that the result of this addition is incorrect, because the sign bit of both addends is 1. That means we are adding two negative numbers. Therefore, the result has to be negative, so the sign bit of the sum should be also 1, but it is 0, which is not. The reason for the invalid result is due to overflow out of the range limits, because with 5 bits we can only manage numbers from +15 to -16, and the result is -17, so out of range. In summary, these are the main conclusions explained in this video. The 2's complement form is particularly useful when managing negative numbers. Computers do not know about the negative sign, only know 0 and 1. A negative number can be represented by its 2's complement. The 2's complement conversion consists in two consecutive changes. First, invert the number, and second, add 1. The 2's complement arithmetics allows to perform a subtraction using the same logic for an addition. While performing binary additions or subtractions, we should always be careful about the range to avoid an invalid result. And an invalid result using n bits can be valid by using increasing bits because, in this case, the result may not overflow. Thank you very much for your attention. Have a nice day. If you like this video, please hit the like button and subscribe for more videos.